Hey everyone, my name is Sahil, and today I'll be doing my report on lab. I'll ask for a brief introduction. For the first part, I calculated the mass of the black hole using the model, and then the second part, I used that mass to calculate the initial velocities needed for the spaceship to come close to the black hole and then leave it. As for any physical models here, we see the gravitational forces between the star and black hole in the first part, and then the spaceship, planet, and black hole in the second part. As for a brief preview of the findings, we find out that the calculated mass is 1.34 times 10 to the 34th kilograms, and then the initial velocities are -4 times 10 to the 7 in the x direction and 2 times 10 to the 6 in the y direction. The part 1 system is just a star and the surroundings are everything else, while for part 2 the system is a spaceship and the surroundings are everything else, which is the black hole, planet, and the space around it. As for the fundamentals, we have Newton's second law, which in this case is momentum. FNet is basically reformatted in the sense that we can do it in change in momentum over change in time, and this is useful because with these values we can plug in FNet into velocity update and position update used in the second lab. We also use the parallel and perpendicular components of force. In this case, they're used to find the aeroscale values to see how large these forces are when you get close to the black hole when you're in the star in the first lab, part one of the lab. And then finally we have the universal law of gravitation equation here. This is used in both parts of the lab. For the first lab specifically for calculating the mass of the black hole, and the second lab to find the net force between all the bodies to do position and velocity update. So here we have part 1 of the code. So here we have this unique seed needed to calculate the unique masses and the velocities. From this we have our given star mass and delta t, and then we use these to calculate the initial momentum and the final momentum. From this we can get delta v and delta p from doing the final minus initial, and then we get dp dt from doing the change in momentum over change in time, which is essentially FNet. And then FNet is used to calculate the mass of the black hole by rearranging the formula on one side and then getting everything on the other to calculate the mass of the black hole. We also calculate FNet perpendicular and parallel here. This is mainly for the aeroscale values on the bottom left, which are written there to show how large the forces are, both parallel and perpendicular, when you get close to the black hole. In this case, the perpendicular gets much larger when you get closer to the black hole and not as large when you get farther away. Here are the results. So when you run, you can see that the perpendicular values get much larger when you get close to the black hole. So as for part 2, this is where we calculate the velocities needed to come close to the black hole and leave it. We use the black hole mass from the previous equation, part, and then we use this mass to calculate the FNets between each of the respective bodies. So for one example, like we used the we calculated the FNet between the planet and the black hole, and then using calculating r hat and r magnitude, the magnitude of r, and we plugged into the universal law of gravitation equation. We do this for all the specific interactions between all of them, and then from this we get FNet, and then we use this FNet value to do velocity update and position update on the planet and the ship to see how they move through space. And as for the results, this is how they do move. In order to get the ideal results, we have these x and y values of speed to get the spaceship very close to the black hole, and then it shoots out away from it. As for any sources of error, we do have estimation. That is definitely an error because we have to round when we do calculations, but in the real world there's no such thing as rounding because values are infinitely precise, so we do lose precision when we do this. As for any further discussions, what does it mean how does the net force and its parallel and perpendicular components differ from the rate of momentum? Well, FNet here is dependent on mass, and in this case, shown in this equation, change in velocity over change in time. This is much different to the change in momentum, where you can simply get that through P final minus P initial over the change in time. So what the individual components of calculations are much different in needing the parallel and perpendicular components. And then from this, and in the change in momentum specifically, you get the parallel of FNet and the perpendicular of FNet to get the true FNet, as shown by the image. And instead, what if we want to look at the black hole in an orbit? Well, I found out that these values work, and then they give that resulting image. Well, that is all for my lab. Thank you.